NH3. The formula is simple enough. Let's see if it's as simple to make. Ammonia is nitrogen combined with hydrogen. We'll start on a very modest scale. We'll try to combine just small quantities of the two gases. This is nitrogen being bubbled into an upside-down test tube. The liquid is a dilute acid containing a chemical indicator. Any ammonia we make will neutralize the acid and cause the indicator to change color. Next, we add 3 times the volume of hydrogen. And now we'll try to combine the two gases to make ammonia. Between the two metal electrodes at the top, we apply a very high electrical voltage. You can see a spark if we dim the lights. And around the spark, there should be a high enough temperature to make the two gases combine. But it's a slow process, so we'll see the film speeded up about 100 times. Look for a darkening of the test liquid. That will mean ammonia. It's slow because, unfortunately, the spark also splits ammonia up. The process will certainly have to be much faster to be of any use on a larger scale. And how can we alter things so we don't need to stop after one batch and start all over again? Well, here's one way. And how to solve the problem that the spark also breaks ammonia up. The answer here is to use a catalyst instead. In the real process, this is a special mixture prepared mainly from iron, which speeds up the chemical reaction enormously. When ammonia is made on an industrial scale, hundreds of tons of catalyst are used in a single plant. But the catalyst is no good when it's cold, so the next improvement is to add a heater. And the reaction is improved again if the gases are fed in at a high pressure. So, add a pump. The real compressor is big and powerful, as much power in fact as 4 diesel locomotives. The tower on the left is the heater. The one on the right is the reactor where the ammonia is actually made. Several times a day, samples of the ammonia product are taken for laboratory analysis. When the ammonia is made, it's at a high temperature, and it's a gas. But here you can see it's been liquefied. In fact, liquid ammonia is extremely cold. You can see the flask frosting up. So to collect and store the ammonia as a liquid, an essential part of the plant is a cooler. By causing the ammonia gas to liquefy, the cooler also has the effect of separating the ammonia from any unreacted nitrogen and hydrogen. Both these unreacted gases would need a much lower temperature for them to liquefy as well. Notice that in this design, we're just wasting these unreacted gases. So take them back to the start of the process and feed them in again. And now, in a simplified form, that's the heart of the real ammonia process. The tower that actually makes the ammonia is only one small part of the whole plant. Most of the plant is designed to provide the nitrogen and hydrogen needed to start with. This is done by processing raw materials. North Sea gas is one of the raw materials. It's very rich in hydrogen. The gas is taken right onto the chemical plant by pipeline. What happens is this. The natural gas is reacted with steam to give the hydrogen and also carbon dioxide, which can be removed later. This reaction takes place in an important section of the plant called the primary reformer. The primary reformer is a large shed-like building. On the inside, it's a furnace. If you look through an inspection window, you can see vertical pipes glowing red hot. Packed inside the pipes, another catalyst to help the steam and natural gas react together. So now the hydrogen needed has been prepared. What about the nitrogen? To get this, some of the hydrogen just made is burnt with air. Air, in fact, is one of the major raw materials for making ammonia. Air is burnt with hydrogen to give nitrogen and water. Coming out at the right now is a mixture of 4 gases. A device called a separator removes the 2 that aren't needed. The carbon dioxide extracted is useful for other industries and is sold. The separator isn't just one unit, but several. The 2 towers to the left are where the carbon dioxide is removed. Now the story is almost complete. On the right, there are now just the 2 gases needed to make ammonia. So, hydrogen and nitrogen are made from natural gas, air and steam. And with careful planning, the proportions of the gases are the correct ones for making ammonia, 3 parts hydrogen to 1 part nitrogen. All we have to do now is add the ammonia making section and join them up. And this really is the complete system, a simplified picture of what happens in the real plant. Very little on the plant goes to waste. Steam is raised using excess heat from the chemical reactions. The steam is used to run compressors and generators, and also as a chemical to react with the North Sea gas. Everything is designed very carefully to make the best possible use of energy and raw materials. It takes days just to get a chemical plant started. So as far as possible, it's never allowed to stop. Night and day, it's watched and cared for, almost as though it were alive.